First of all, thank you for inviting me and Energinet to this webinar. It's super exciting, and today's topic from our side will be on how can we balance a renewable-based grid, and what transition is the electricity system going through right now from dispatchable generation or production to more dispatchable consumption, and how power to X can play a key role and industrial flexibility in that transition. Energinet, where I'm from, to those of you who are not familiar with the company, is a transmission system operator in Denmark, where we operate the transmission grid for electricity and gas, and we also develop it. And hopefully soon we will also be the transmission system operator for the future hydrogen backbone, which a lot of power to X developers hope that will be realized. So we are owned by the Danish Ministry of Climate and Energy and Utilities. Hence, we are working for the society. We are not here to make profits. We are here to lower the tariffs for the entire society of Denmark. With that said, I would like to go into what transition have we seen in the Danish electricity grid, or what are we progressing towards 2040. What you see on this slide, it is that the amount of dispatchable power, that is the thermal power capacity, the dark green one, it is decreasing throughout time. Hence, we will lose dispatchable power in the Danish electricity grid. On the other side, we will see a lot of intermittent fluctuating solar and wind, the yellow and the light blue ones, penetrate into the electricity system. So soon we will have an electricity system that is 100% run on renewables with marginal parts of thermal capacity, and of course still some interconnector capacity to our neighboring Nordic countries. And if we deep dive a little bit more on this transition, then, and I'm very sorry for English speakers here that I didn't manage to translate this to English, but I hope that you can follow the narrative anyway. What you see here is the amount of onshore and offshore wind that has been installed in the Danish electricity grid in gigawatt on the Y scale, and that is towards 2025. 12 gigawatt summed. But this is not where we should end, because the Danish Energy Agency has made some progressions or some estimates on the future, stating that we will have around 30 to 40 gigawatt of solar capacity, the yellow one, in 2050. And we will also have a lot of offshore wind, the blue one, and onshore wind, the green one. So there will be a lot of renewable capacity connected to the grid. And that is the one side of the story. The other story is how will the electricity demand follow this? Because if there's no increase in electricity demand, there will be no business case in setting up renewable energy capacity. And this is where it gets very interesting. What you see on this graph, it is in terawatt hours per year electricity consumption from different sectors, where we from 2005 until 2025 have not seen a major increase in electricity consumption in the Danish system. But from now on towards 2050, we will have several sectors almost exploding in electricity demand. And those are, the gray one is the classical electricity consumption. It is not the expectation that will increase a lot. But if we then go into the yellow one you see here in the bottom and the green one, those are the district heating and the transportation sectors. The electricity demand from those will increase a lot. And then the blue one, it is the data centers. We will see a lot of data centers coming primarily in DK1 in Denmark in the next coming years, and they will consume a lot of electricity. And we hope that they will, to some extent, be flexible in their electricity consumption. But to be honest, we actually don't know it. And then we have the power to X sector. That is this gray/light green part. You can see it is almost the biggest share in this chart. And the estimations for power to X, it is that it will be flexible and it is price sensitive. And that is super good for the green transition, because we would not be able to include all this capacity into the electricity system if none of it was flexible. And then just to wrap this slide up, this is a 400% increase in electricity consumption over 25 years. So it's drastic changes that are required within a relatively short time frame. And if we then deep dive into the power to X part and also in general industrial flexibility, there are, at least for power to X, 3 key elements that power to X can help and support the electricity system with. The first one is that when the power to X industry starts to accelerate, it will support also the integration of renewables, because it will increase the price, the day-ahead price, and that will make it more attractive for renewable developers to set up solar and wind capacity. And it would also help utilizing the utilization of the grid capacity if these power to X plants are positioned in smart ways and strategically positioned in the grid. And the third part, the one that I will be focusing on for the next 10 minutes, it is how can power to X help support balancing the electricity grid, because there we see great potentials to achieve. So going into what does it actually mean, balancing an electricity system? In short, it means, as Bo said in the beginning, that the amount of electricity production that is produced at any given time, it needs to match the amount of electricity consumed at any given time. If there's a mismatch between the production and consumption in the Danish electricity system, it will affect this weight. And then the frequency in the electricity system will not stay at 50 hertz. When the frequency is at 50 hertz, then the frequency oscillates 50 times per second. We can't see it with the bare eyes, but that is a steady state of the system. If we have too much production, then the frequency will deviate from 50 hertz, and that is what we try to avoid. So going into how have we traditionally balanced the electricity system, what you see on the left side of this picture, it is that whenever we had a need for production to increase its power, then we could relatively easily do that in the traditional/old electricity system. So here in the figure, when the need was that we need to produce more, a gas power plant could just ramp up. And in another period where there wasn't that much consumption demand in the grid, then the production could just curtail down. And this meant that the dispatchable production was like the key in the electricity system. It was also what led to imbalances in the electricity system, because there were no renewables. So it was only when a production plant in Aarhus or Aalborg maybe went out of operation, then we had an imbalance. And this system was also characterized with a lot of spinning reserves. There was a lot of dispatchable power plants in the electricity system, and that made the electricity system very resilient towards disturbances, etc. But the electricity system that we are moving to now is a lot more intermittent renewable electricity production. So now the consumption actually has to follow the production instead of vice versa in the traditional electricity system. And now what we see of the types of imbalances that can occur in the electricity system, meaning mismatches between electricity production and consumption, those imbalances are now often caused by prognosis errors on renewable electricity production. So some balance responsible parties, they might say, I put in a bid for 500 megawatt for this wind park in the day-ahead market. But when we get to the actual moment of time where you need to produce 500 megawatt, then they only produce 300. Then we have an imbalance of 200. And that imbalance needs to be taken care of. And then I would like to go into what are the challenges of this green energy transition, some of the key challenges that we from Energinet see. In general, as you see in this picture on the upper left part, when the amount of renewable energy increases, then we see larger imbalances. And that is due to this fact that it is hard to prognosis or forecast the electricity production from wind and solar with a very high accuracy at all times. That is a difficult task. So greater imbalances emerge, and those Energinet needs to take care of. Another point that has shown in the last couple of years, it is that these solar parks, which you see around the country, the fluctuation in power production from these can be very significant. What we show here, it is how much a solar park of 140 megawatt in capacity can actually fluctuate within a few minutes. It is crazy. Oh, sorry, this is throughout the day, but it is crazy magnitudes that can occur, even though the time is 12 or 13 during the midday. And then the last challenge that I would like to highlight, it is that with the penetration of renewable electricity capacity, we will observe an electricity system that has lower inertia. And inertia simply means that we have less spinning reserves in the electricity system. So when we have a disturbance and a big power plant, a big nuclear power plant in Sweden or Finland is going out of production in DK2 and the Nordic electricity system, we will see the frequency drop a lot before it starts to restore again. And how it restores, we get back to that in a moment. But this is a consequence of the green transition. And how do we accommodate with these challenges? Well, we have designed ancillary service markets that cope with these challenges and mitigate them to the best possible way. And here you can see we've put these different cars or automobiles on them, and that is when we go into the characteristics on them, we can see that they differ a little bit, these ancillary services. But before jumping into the exact ancillary services, then I would just like to clarify that, of course, as Bo said in the beginning, when you have flexible consumption or flexible production, you can offer that flexibility into the day-ahead market. That is the implicit flexibility. So you can produce or consume at very attractive hours. But what I mean here about flexibility, it is the explicit flexibility. That is the ability to AS ancillary services to offer your flexibility to the TSO, to the Energinet, to stand by, that is the capacity market. And then if a need occurs, an imbalance occurs in this exact moment, there will be an energy activation market that will ensure that this flexibility is activated. So now I'm going into the explicit flexibility and keeping the implicit flexibility out of the picture. The way the ancillary services markets are organized in Denmark is in a DK1 bidding zone and DK2 bidding zone, where DK2 is, due to historical reasons, a part of the Nordic synchronous area. So DK2 has more in common with Finland and Sweden than they have with DK1 actually. And then DK1 is connected to the continental European electricity grid and has more in common with Spain or Portugal when we are talking electricity system terminology. And here we have different ancillary services in the two bidding areas just to ensure or to reflect that DK1 and DK2 have different characteristics. one way to differentiate the ancillary services, it is that some of them are what we call energy/capacity products. Those provide a lot of energy when they are activated. That is the MFRR and AFRR markets, whereas the FCR market in DK1 and the FCR markets in DK2 are frequency markets. There you need to provide less power, but you need to provide the power very fast. And then I like this terminology on how to make money from the ancillary services. That we look at how does ambulances work in the world. For instance, Falck. It's a company in Denmark. They operate ambulances in Denmark, and they get a capacity payment for sitting and drinking coffee, being ready inside the house where they have their truck and all their material. So they get a payment for standing ready, €1 per megawatt. But if there is a fire and they need to go out and mitigate a fire, mitigate an ambulance, they get an energy activation, and then they get an activation they get a payment dependent on how much fire do they actually mitigate, and that is the reason for €1 per megawatt hour payment. So that is how industrial flexibility and Power-to-X can make money. It is both for the capacity payment and the energy payment. And then I would just like to show you guys that these minimum bid sizes, how much flexibility you need to accumulate to bid in, are actually pretty low. In DK1, they are 1 megawatt. In DK2, they are down to 100 kilowatt. So you don't need to aggregate a lot of flexibility before entering these markets. That is something that Energinet works a lot for, to increase and unlock more flexibility in these markets. And then before wrapping up, I would just like to show you the characteristics of these different ancillary services and how fast you need to react. Gunnar will get back to how this matches with Power-to-X, but here I will show the market-wise that when we have a disturbance in the electricity grid, then we have a few ancillary services, the frequency-based ones, FCRD and FCIN, that needs to react within seconds or a few minutes. That might not be feasible for Power-to-X or industrial flexibility to meet those capabilities. But then as the time goes by and we need more energy-intensive ancillary services with the AFR market and the MFR market, then more energy needs to be provided. The integral below the power curve needs to be bigger, and there the AFR market and MFR market can really provide some energy, and there industrial flexibility and Power-to-X can play a key role. And then I just wanted to show you that last year we actually pre-qualified, or we accepted 700 different unit/aggregated portfolios to deliver ancillary services in Denmark. And those types of technologies could be power plants, electric vehicles, batteries. Even one electrolyzer in DK1 is ready for AFR participation, solar and wind. So we have a lot of different types of resources participating. My last bullet, it is to say, okay, this ancillary service market, is it saturated? Is there room for more? Can Power-to-X come and play a role? And yes, Power-to-X can come and play a role. This is our projected need for ancillary services towards 2040. Right now, we procure around 1.8 gigawatt of summed ancillary services per hour across all ancillary services. So we have 1.8 gigawatt of these Falck helpers or these firefighters ready to be activated, and this amount will just increase towards 2040. So there is a need to unlock more flexibility. And this leads to my final remarks. I just wanted to end with the final note that the amount of dispatchable power production is declining over time, so flexible consumption needs to close this gap We need to get the flexible consumption unlocked in this transition. And we as Energinet are technology agnostic. So we don't care whether you have an aggregated portfolio or a big plant or whatever. We want all the flexibility that we can harvest as possible, as long as it of course meets the technical capabilities that we set forward when participating in these markets. And then it's super important to remember that when you participate in ancillary services, it is a way of hedging towards volatile electricity prices. If you only go to the day-ahead market and procure your electricity there, then you're 100% exposed to volatility. Here you can make an extra revenue that can increase the profitability of your business case. And the last point, of course, there's competition, but the need is rising. So we really need the flexible consumption to come forward. I must say sorry that I used all my time, but this was my final remarks of the presentation, and then I hope we could have some good discussions in the end of this webinar. And Gunnar, maybe you can proceed from here.
Yes.
So I hope you can already see the screen and also the laser pointer.
Yes.
Perfect. Then we can start looking a bit more into the techniques. So when we discuss Power-to-X today, then it is very much focused on this part, which can be described as a chemical process technology. So the X is basically any kind of synthetic energy carrier or fuel in gaseous or liquid form. So hydrogen, methanol, ammonia, and even more complex things. So it involves a lot of electrolysis, chemical synthesis, but also the distribution, conversion, and storage of these gases and liquids. So the first thing to know is that, of course, chemical process industry has a long history and a long tradition. And even if you consider the flexibility of chemical process industry, then also this is, at least in academia, a well-known topic. And over the last decades, basically all possible aspects of these large chemical process facilities in terms of flexibility have been discussed. That starts from where to place such a facility within the grid in terms of the neighborhood to energy supply, but also off-taker, distribution networks. It has been discussed how they can be timely more flexible as a consumer, as a load. So all these aspects have been discussed. What is new is, of course, where Simon already set the stage, is that today we electrify much more of these chemical process facilities. So it is really that we are dependent of green renewable electricity in vast amounts to produce all these chemical energy carriers, which can then be used on the other side as industrial raw materials, green fuels, energy storage, and other assets.
You're muted, Gunnar.
Why that? Oh, sorry. How long have I been muted?
Just 10 seconds. It was not a long time.
Okay, then it's fine. Then I go back to the slides. So it was just because I heard an echo. So the first thing I would like to now dive a bit more into is the electrolysis part, which sits at the very beginning of most of these Power-to-X value chains, and is also the primary consumer of electricity. So if we have a look at this an example electrolysis stack, then these items are typically built up quite modular. So you have these electrochemical cells that are then stacked up and also connected electrically in series to ramp up the voltage. And then you typically increase the size of the different electrodes to increase the current. So you can build your electrolyzer adaptive to the application where you want to run it. And then it's, of course, the basic idea is you take water in, perfectly or almost pure water, and then by the help of electricity, you split it up into hydrogen and oxygen, which can then be used as sustainable energy carriers and raw materials. And now, of course, since we use electricity for splitting the water, so we are a large consumer, Simon showed very well where we expect Power to X to be on the consumer side in the future in Denmark. There is, of course, also the immediate idea that we want to try to transfer some of the cost that we have by purchasing electricity from the grid to split water into a revenue stream, that we not only produce energy carriers, but we can also participate in the ancillary service market. And there has been a quite famous study a few years ago here from Denmark, where a 10 megawatt alkaline electrolysis system has been considered to participate in the Danish grid. And it could be shown that on the one side, of course, the electricity cost can sum up to even above 50% of the final hydrogen production cost, so a considerable amount in the production cost for your primary commodity. But also, the study showed that it is theoretically possible to increase the potential annual revenue of these electrolysis systems by up to 72%. So almost, if we are rounding up quite a lot, almost a doubling. So that is, of course, quite some motivation to look into not only being a flexible consumer or dispatchable consumer, but also participating in the ancillary service markets. And the next one is a similar picture to what Simon was shown before. So looking into how are the different ancillary markets or the different services that we can provide, how are they built up? And the study that I was just referring to, they were basically looking up into the FCRN and partly the FCRD upwards and downwards markets for estimating the potential revenue for an electrolysis stack. The important thing is now that these revenues are not come for free. It is, of course, that when I want to participate in these markets, I need to comply with my technology to all the stringent requirements that the local TSO or even the branch of TSO is giving. And that leads us to the boundary conditions that the different electrolysis technologies that we actually know, that they also have different technical characteristics. So this is a more qualitative comparison between the group of polymer-based electrolysis technologies, so the polymer electrolyte membrane, the alkaline electrolysis technologies, and then the solid oxide electrolysis technologies. And here you can already see, I try to compare a bit of the key characteristics with respect to flexible operation, that we can see they are quite different in their behavior. So even if the PAM is quite flexible and has a comparatively good cold start and minimal load capability, then it might be that the efficiency at the cost is not completely on par with some of the alkaline technologies, which are then challenged by the minimum load the system can actually ramp down to, also in terms of ancillary services. And the solid oxide electrolysis technologies are currently not so much considered for dynamic load. That also is due to their lower technology readiness level. And the main issue that since they are operating at so high temperatures, above 600 degrees Celsius, dynamic operation of these stacks typically causes thermomechanical disturbances and gradients within the electrolysis stacks, which can be very harmful. But here I can also mention that the DynFlex project Grace was mentioning before, where we all are part. We also have a partner, a Danish partner, Dyn Electro, and they are working on a special novel control technology, which actually provides the possibility that the operational load range and the cold start and flexibility behavior of solid oxide electrolysis stacks can also be increased a lot, which provides them a potential future place within the ancillary service markets. Our problem is now that there are not only these technical characteristics and drawbacks, and on the one side, the cost for the electricity and the potential revenue. It is also the thing that as other electrochemical energy conversion technologies, also electrolyzers, facing certain aspects of degradation. And I tried just to summarize a few of the main degradation aspects here that are partly also special for individual technologies, but in general, we find them more or less dominating in all of the different technologies. And our problem is that they are increasing whenever we operate the electrolyzer more flexible with respect to a more dynamic load profile. And that rises the situation that in many of the current large-scale facilities, when we only considering them for producing hydrogen, the stack replacement costs will sum up to from roughly a third to almost half of the overall capital expenditures for the whole plant. And we also see that dynamical operation accelerates this degradation by a factor between 1.5 to 2.5. If we really stress these electrolysis stacks, we can even accelerate the degradation by a factor of 5 or 6 or 8 if we want to, but this is a quite solid average. We actually find a lot of different electrolysis stacks in practice, and you can see here that, for example, this example of a pressurized alkaline electrolysis stack, this is the real physical device here from Hydrogen Pro, and you can see the people as a scale. It's a nominal power capacity of roughly 5.5 megawatt electrical. And here you see some colleagues from Green Hydrogen Systems, which are standing in front of their pressurized alkaline stacks. And it's not the case that the people from Green Hydrogen Systems or the former colleagues are simply much taller than the Hydrogen Pro colleagues. It's simply that this stack is only 1 megawatt of nominal capacity. So already scaling this stack has huge impact of the different characteristics in terms of both degradation and flexible operation. And then, due to practical reasons, you can imagine that building a stack even larger than this one gives us some issues with transporting them on a truck or even maintaining and servicing them within a facility. So when we build larger facilities, like this conceptual sketch here for a 100 megawatt hydrogen production facility for a steel manufacturer in northern Germany, this actually incorporates these Hydrogen Pro pressurized alkaline stacks, and we see 20 of them in 10 groups of 2 stacks each. And you can see here that in a practical system application, also things like the water treatment, the gas separation, the gas purifier, compressors for the gas, power electronics, and a cooling system also have a huge impact on the overall system power demand profile and terms for flexibility. And here it is also sometimes due to practical reasons how you actually scale these different subsystems or balance of plants items. If we have a single DC-DC supply for each stack, or if we connect several stacks to a common DC-DC supply, or if we have one compressor or 2 compressor for the whole system and a central cooling systems, all these things are huge design parameters in a practical system design, which leads to a lot of flexibility, complexity, or potential. And if we abstract it a bit more, in practice, we basically always deal with several electrolysis stacks that that constitute a larger system. And our issue is that we currently see many systems that consist of many stacks due to practical reasons, transport, implementation, and maintenance. But then in terms of the control strategy, the facilities put huge effort into the system control to make all of these stacks act like a virtual large single stack. And this really is a lot of effort, and it cuts down some of the flexibility potential that we actually get, since we can control the individual stacks and also slightly parts of the individual balance of plant individual or independent of each other. And that is actually something that we are currently looking into in this Dynflex project, where we develop a kind of stack management system for these multi-stack electrolysis arrays. And you can here see that it is not only that we build a system consisting of several stacks, it's really that we monitor all the different parameters. That means having real-time full control of the individual pumps and valves and heat exchangers, and also how the stacks, the electrolysis stacks, are performing. And with all this gathered data, we can then, in the actual management system, do some kind of diagnosis and find out how do the systems behave, what kind of well-being do they have. And with this information, it's actually possible to calculate or predict in the future, if I now want to react to a price signal from the ancillary service markets, what will it actually cost me? How will it affect my remaining lifetime? And with this information, we can then establish a quite optimal control strategy, which try to follow a predictive load signal, and then controls the individual stack in full load, part load, or even standby operation mode. Here exemplified just for simplicity with 3 stacks. And you can already see here that with these procedures, we can also share the actual operating hours in general, and also the individual operating hours at different load states between the stacks, so that we can achieve a quite homogeneous degradation and avoid that a single system is overloaded too much, and then gives the risk for providing unscheduled downtime of the overall system. And current simulation and also first results, experimental results, and on smaller systems, actually suggest that we are able to reduce the OPEX when running these multi-stack electrolysis arrays between 38 and 59%. And if you now bring all the different numbers together, okay, we have a potential of increasing our revenue by up to 72%. But if we increase or accelerate our degradation by more than a factor of 2, then the degradation will eat most of the extra revenue. But if we now, with optimal control, can not only extend the lifetime by reducing degradation, but also reducing the operational expenditures, then it is easier to actually harvest some of the potential revenue from ancillary services for being actual revenue for the system operator. And when we now go back to the initial value chain diagram, I must say that now I only looked a bit more in detail onto the electrolysis, but the overall power to X value chain can be much more complex. So if the electrolysis, for example, is only part of a methanol or ammonia synthesis plant, then these reactors also need to possess a certain flexibility that matches those of the electrolysis systems, or the overall system integration needs to have some decoupled infrastructure in terms of intermediate storage or thermal storages for the heat for some of the Haber-Bosch reactors and things like this, to avoid that a rigid synthesis reactor further down the value chain actually prohibits that we can utilize the electrolysis flexibility for ancillary services. And before I conclude, I would like just to mention that from a technical perspective, there are different technologies that actually can participate on the ancillary service markets. Simon was also mentioning these, I think, 700 different assets that have been just approved over the last period. And here you can see that if we, for example, compare electrolyzers, stationary battery systems, and also large-scale heat pumps, that some of the technical characteristics that are important for delivering ancillary services, they might actually look similar, but overall said, there is actually so much difference between these individual technologies that I would say they have more a complementary positioning in the market and should also be considered as being in constructive interference, as if we always should try to bring them in direct economic competition to each other. And with this, I would like to conclude and give you some key takeaways at hand. So I would say that flexible operation for electrolysis actually is the technical reality, but it comes at a cost. So it's important to actually make sure that revenue increase from ancillary services is not be eliminated by accelerated degradation if you leave this unmanaged. And the thing is that also the choice for electrolysis technology and overall system integration is quite dependent on what kind of market you addressing for the ancillary services, if it is FFR and FCRD, or if it is more FCRN and MFRR, as Simon was showing, then the electrolysis technology becomes also maybe more a Formula One car or a normal passenger car. The multi-stack array system design and the predictive management seem to provide quite some good optimization opportunities, because we simply transform this stack degradation from a hard technical constraint or barrier to a decision variable within a management system that we can work with. The overall system design and integration of electrolysis together with synthesis and other subsystems of larger power to X facilities, this always imposes some constraints, and it requires that we actually consider this from the beginning to make sure that there is decoupling infrastructure and the system really can, or the plan can really work as expected. And then power to X demands a complementary positioning in the ancillary service markets, and it should be seen in constructive interference with the heat pumps, with the EV charging, and with the electric boilers and the battery system, and not necessarily always as a main competitor towards. And with this, I hope I stayed roughly within the 20 minutes. And now Frederick has the honor to bring everything together and tell us how we can manage this.
Yeah, so as Grace mentioned, I will try to talk about this, how to bridge the gap between the market participation and the processes that can participate. So yeah, I will talk about the screening of industrial flexibility for market participation, and I will talk about this process to market tool. And then, yeah, I'm Frederik, and I work here at the Center for Energy Informatics. First of all, this work is conducted under the DINFLEX project, and here at the center we are responsible for the work package 6, where we look at evaluating Power2X's participation in the electricity market. And we do this by modeling the mapping, and then we look at the business potential and potential barriers for participation, and then we also look at different strategies for participation under current and future market participation. And then for this presentation, we will talk about the process to market tool and how it's screening for industrial flexibility. So my plan was to talk a bit about the background before going into the tools, but I think we got a bit up to speed by Simon, so I will skip the slides for now, and then I will just briefly talk about that the consumer side participation in the electricity market can have various advantages. So we have heard it a bit before, but the consumer have some additional revenue, the grid operators will have less need for physical assets and lower grid congestions, the market operators will have some higher liquidity in the market, the renewable production units will potentially have increased operation time, and then the governments will have less need for subsidies, and yeah, of course, the goal of having a higher penetration rate of the renewable production. So the demand response by industrial consumers are seen as a path forward for helping the market to stabilize the grid. That is due to the fact that they are large consumers, so they have a lot of capacity and high energy needs. They are planned loads, so they can potentially schedule their productions smartly to help the grid and participate in the market. They often have these ICT equipments already installed, so they can actually control their production facility, and then they are price sensitive. So if they see a profit maximization pathway for participating in the markets, they will probably do that. And then, yeah, here's just some pictures of the processes we have worked with here at the center, as Bo also pointed out. So let's go into the tool. So this process to market tool is a techno-regulatory feasibility screening of market participation. It consists of some inputs where there is a questionnaire. This questionnaire is trying to obtain some technological constraints, some logistics constraints, and then also some willingness of participation. And the output is then that each submarket is compared and scored between the submarkets, the parameters, and the process parameters. This tool is built upon this process to market matrix mapping, which was developed here at the center. And the tool has these three main steps. So the questionnaire is filled by the user to obtain the process parameters, and then the market data is then compared with these process parameters, and we then obtain the result. The questionnaire part is divided into 5 sections, see here in the tab up here, and these are then divided furthermore into questions with a total of 32 questions, divided into facility logistics and so on. And then the market data section, which is for now preloaded with the electricity market data for Denmark. It then allows the user also to edit and delete markets if they seems to do that. Yeah. And then lastly, the results section of the tool is seen here, some of it. So the market parameter scores are shown as a radar plot, and also the tables here. And the same goes for the flexibility parameter scores. looking the same. And then furthermore, you can go into each submarket that is in the tool, and then you can see this matrix of how the process parameters are compared with the market requirements, and see the total scores. There are some advantages and disadvantages of the tool. So first of all, it is based on a thorough methodology. So this process to market matrix mapping is peer reviewed. It takes a lot of dimensions into account. So we take both the technical, operational, and organizational dimensions, and also some willingness. And then it's an early stage screening of market participation. And also it's a web-based tool, so there is no local installations or anything, so the stakeholders can engage quite easily with the tool. On the other side, there is also some disadvantages. So it's quite complex, the questionnaire. There have been some feedback from users saying that it's a bit time consuming to fill it out, and some of the questions are also a bit hard to understand. Furthermore, the transparency of the tool is lacking a bit, so it's not always clear why one market is scored in a certain way. So you have to kind of go back and forth between the questionnaire and the results to kind of figure it out yourself. And then lastly, the result is presented as I just showed, with the radar plots and tables, which can be a bit hard to interpret as a user, especially if you're a non-technical electricity market user. And yeah, this makes it a bit difficult for the user to make like a decision for going forward. So therefore, we have looked into making a version 2.0, and this is still this techno-regulatory screening tool, but it then tries to address these disadvantages from the version 1. So we are trying to simplify the questionnaire, increasing the transparency of the tool, and then making it more interpretable for the results section. And yeah, this is still in the prototype stage, but it's ongoing development, and it's also web-based. So here we see the overview of the tool in the upper part of the tool, where we have a questionnaire over here, and then the list of markets. The questionnaire is divided into 6 questions. So compared with the 32 questions for the version 1 tool, it's quite a reduction. And these questions tries to obtain the regulatory requirements of the markets, or not of the markets, but of the process, what it can do. So the location, the capacity, the RAM time, the duration, utilization of the process, and how they schedule the production. And here we have in the questionnaire included these tooltips. So if the user don't understand why this question is important or so on, they can hover over it and get some more explanation. On the right side, we have this list of electricity markets, which is again the electricity markets in Denmark. And for this questionnaire inputs, all the markets are feasible for now. But if I change it a bit and, for example, say that I'm in DK1 and I have a ramp rate of 5 minutes, then some of the markets are like crossed out. So we see here that, I don't know if you can see it, I hope so, that this market is not feasible to participate in, because the question 1 due to location. And then you can also hover that and see a bit longer explanation of why the market was excluded. And then to the results. So this section is divided into a feasible market list again, a potential revenue estimator, and then an overview of pre-qualified capacity volumes. So the lists from just besides the questionnaire is expanded a bit here. So we have tried to map the markets into a low, medium, and high risk category, and then there is also some more explainable text about the markets, and then, for example, for the ancillary service markets, it also tells if the users can participate in both up and down regulation markets if it's asymmetric activation. And then the tool also have this expander where we can see why the 5 other markets were excluded. Then the potential revenue estimator is shown here, where we try to get some kind of order of magnitude screening of the tool or the markets, what the potential of revenue can be. So all the feasible markets will be shown in the figure, and then if you participate with all your available capacity in that market, you could have this potential revenue. And yeah, this is for December, the whole of December participation in 25. And then just for comparison, if you procure your day ahead or your energy in the day ahead market, just at a flat rate of consumption, you would have these expensive. So it's kind of comparing expensive with revenue. And then lastly, the results also have this pre-qualified capacity table. So here on the columns, all the feasible markets will be shown, and then the rows here is divided into technologies. So yeah, and this is from the Energinet. I think Simon also mentioned it a bit, but then you can see what technologies you are competing with, and then we have also included what Energinet forecasts to procure in 26, and then you can kind of see that, okay, the MFFR up, they procure quite a lot, so maybe that's easier for participating in if you are, yeah, so you're probably easier for getting your bid accepted. And then to conclude, so the disadvantages of the process market tool have been addressed in this version 2.0, and this shows the direction for easy screening of industrial processes participation. And this screening is, of course, the pre-step before going into a more in-depth simulation of market participation. So what Gunnar was talking about with simulating and controlling the plant maybe before that step. So instead of having to simulate the whole plant with all the electricity markets, this tool could be a pre-step before that. So you only have to maybe simulate a few of them in your whole simulation, such that you don't need to do to all the markets. Yes, and this was my presentation. Thank you for attending.
Okay. So as I said, we prepared 5 questions, which is, of course, focused on all 3 presentation aspects. So the first question, actually, I think, Simon, you might can find yourself. And basically, although you mentioned about these potentials and rising need of this ancillary services market, but actually we can see is still also what Frederick shows about this pre-qualification technologies, which is not in very much provided by the demand side, demand side participation. So what Energinet's plan to, from the regulatory or from market design perspective, and trying to motivate this and unlock this demand side participation?
Yeah, that's a great question. Great. I think I will put two overall perspectives on it. The first one is the market design part. If we, for instance, take the AFRR market, then some of you might remember that a few years ago, that was a weekly obligation. So when you bid into AFRR capacity, you needed to have that flexibility for a week. That was a huge entry barrier because no one could participate except one or two big PRPs in Denmark. And now it is a asymmetric, hourly based market, and that has really promoted a lot of flexibility to come into play into the AFRR market. So that's at least one thing Energinet has done. And if I may say one more, it is that if we look at especially the distributed demand side flexibility, like electric vehicles and individual heat pumps, etc., then there also needs to be more cooperation with the distribution system operators. We see a lot of countries in Europe where distributed flexibility actually participate in local flexibility markets. That is not a thing in Denmark. There are no local flexibility markets in Denmark where you can offer your EV or heat pump capacity as an individual owner. So more cooperation between the TSO and DSO, that is really also a fundament for unlocking more participation.
Super, thank you. Is any of the audience also have some question regarding this topic or something else? And you can put into chat or you can just speak out. Okay, so seems like you covered all. So the second question is basically, Simon, you mentioned that also what Frederick mentioned about this pre-qualification. And so basically is we see is quite complicated in a way of you participant, actually you have a have this risk of not be qualified, and also even you qualify, you will not going to be activated. So there's quite lots of this kind of risk. And also, which is you have one colleague before, she also looked at about this can so-called the participants barriers to understand our participants to the ancillary services market. So whether in Energinet or you think there's any way we can simplify or make this a standardized, this pre-qualification for these non-traditional resources like Power-to-X and storage and hybrid systems?
I can start off, and then maybe Gunnar and Frederik has some
Yes.
good supplements on that. We have actually done a lot to differentiate between what are classical units, power plants, and then also these distributed flexibility. And that is simply to promote that, okay, distributed flexibility, they need a forecast before they bid in. They need a baseline, like a reference power. What would you have consumed if you didn't participate in ancillary services? So we have done a lot, but what I think could make very good sense in this essence as well, and Gunnar, maybe you can supplement that is that, for instance, for the Power-to-X, we don't know how fast they can ramp. We don't know what is the minimum load. Can the rest of the plant or the hydrogen production facility can that ramp up as well when the electrolyzer ramps up? So I think there needs to be more investigation into these different Power-to-X technologies, whether they can actually meet the requirements, so it becomes more. So each time a Power-to-X facility comes to us, it's just like an electric boiler. Electric boilers, we see them in hundreds and hundreds pre-qualified for ancillary services. And that's because the balance responsible parties, they are familiar with them. They know when they give them a set point signal, it will reach 5 megawatt within 3 minutes. They know that. They have that knowledge. But does that knowledge exist on the Power-to-X domain? Frederik, Gunnar, maybe you can... I think that is the essence.
I think that the question is going to be Gunnar, because of Frederick and me actually is contact Gunnar and discuss with Gunnar regarding this, and which is Gunnar gave us a very detailed explanations, but which is the the answer can say depends. But now I think Gunnar have the opportunity to tell us whether it is possible for us to have a much easier way to know whether the technology, I mean, the systems can be pre-qualified, easy to just give it to EnergyNet.
Cool.
So Gunnar, can you say something about this?
Yeah, I start again with it depends. No, I think from a technical perspective, I must say we are in general with some of the technologies that are involved in these power-to-X facilities. Also, when we consider hydrogen, methanol, or ammonia as long-term electric energy storage and some of the hybrid systems, we are not there yet. Where we are with batteries and heat pumps, so we do not know as much. But I think we have learned something from the other technologies, so that we need well-defined parameters, so like a state of charge or a state of health from a battery system that can be shared via the battery management system. There, everybody can get an idea, okay, what is the nominal power, how much energy is left, and how likely is it that the battery will participate. So these are the technical parameters, like a state of health for the electrolysis system or something like this. That is, we are working on it. We are not completely there yet. And I think over the time, some kind of definition will be consolidated that is also shared. Another aspect that is a bit more tricky is that if you, for example, consider a battery which is charged by electric energy, keeps the electric energy maybe for some arbitrage markets and things like this, but also delivers electric energy back to the grid. This is the form of energy, so the tradable commodity is not changed. And this is, of course, a bit more predictable because we know that the battery will stay in the electricity market. A power-to-X facility can be more complicated because there might be different value streams and different tradable commodities. I must also assume I don't think that anybody will build a large-scale power-to-X facility for the primary target of delivering ancillary services. This will always be a secondary or tertiary market. And that means when we do not know about potential other revenue streams, it is a bit more risky to predict how the people will react, because if the electricity prices is rising, and we expect that the power-to-X system will just ramp down, but if the price for hydrogen or ammonia or something else is rising even more, and we need to fulfill an off-taker contract, then we can also assume that the power-to-X facility will not necessarily ramp down. So these aspects there, we are still negotiating if there is some kind of techno-economic data that can be shared at a common platform, maybe with some anonymized parameters, so that actors, stakeholders like EnergyNet can access this to de-risk their prediction of the behavior without that the power-to-X facility operator needs to provide too many sensitive information. But this is very, very early stage, as to my knowledge.
Great. I think if I may, I would like to ask Gunnar another question, which we discussed before, but maybe now you can have a better answer, because before actually we discussed about their electrolyzer, there's lab facilities like also DDIU has. But when we're talking about this participation to the Ancillary services market, which is basically the real power-to-X facilities actually in operations, and that is actually due to the size, actually due to the different technology and different operations. Actually, what you measured or test in your lab will not be so easy to just how to mirror about what it in power-to-X in operations. So that is actually is also difficult to understand what this qualifications for the ancillary service market. So now I would like to ask you whether this kind of gap between the lab facilities and also the facilities in operations, whether there's any way for us to fill the gap or somehow like trying to predict based on the lab facility performance.
Good question. So the positive aspect is that the smaller items or the smaller assets that we have in our lab facilities, they are actually good for us to develop these control systems that can take all the parameters in technical parameters from the system, electricity prices, other control parameters. So because the smaller assets typically react faster. But they have all the different valves and pumps and things like this, only smaller. So we have all signals, so we can very good develop our algorithms. But it's not so easy to simply scale up from a few kilowatt in our lab to a few hundred megawatts because new aspects are coming in. The major aspect is actually that many large facilities are not in the first instance looking completely into maximizing revenue to the extreme extent. In the lab, we are often trying to get efficiency and performance and thing to the absolute optimum. But we see in discussions with large plant operators that they, of course, want to have a good revenue and a good performance and operation. But it's more important for them to prevent unscheduled downtime and unscheduled maintenance, because a few days off where they cannot participate in the market or not actually supply their off-taker contracts can be much more expensive than a few percentage in efficiency or revenue throughout the rest of the year. So that is a bit more predictive operation, predictive maintenance, which has more focus than efficiency. And this is also quite hard to test for us in the lab because system is smaller and we often have it hard to artificially provocate these failure scenarios where we actually can test this, because this is expensive, this is sometimes also dangerous, and therefore what we are trying to establish in Europe is that we have some certain infrastructure scale test facilities with respect to electrolysis. We don't have it in Denmark, but we have some in Germany, where we can then have collaborations with the German partners like Fraunhofer, for example, which have test facilities with large electrolysis stacks or electrolysis systems, where we can test in a bit more a closed environment, a bit like even a pre-step to our green lab in Skive. But then we have the possibilities to also test and pre-qualify things on larger scale, which are more reasonable for large-scale systems. We know it in Denmark from the wind power test system of the Lorg facility at the Lindø Værft, where we can actually test in a simulated environment almost full-size large offshore wind power plants without we necessarily need to harm the grid or destroy a real wind power plant somewhere else.
Good, thank you. Very comprehensive. So then actually is one question which is also when the market, I mean the process meet market, which is Simon already mentioned about, is he's talking about this explicit flexibility. So it means actually is we cannot manually just stay there and turn on and turn off, right? So then actually we would like to know, of course, maybe Simon, you get more information, inside information. So how close are we to this fully automating the data exchange between industrial operations and market platforms?
Yes. With regard to data exchange, we can have two concrete examples. The first one is the bidding data. Like how do you bid into these ancillary service markets? And that is, for the majority of BRPs, balance responsible parties, fully automated. So a lot of them, they set forward like a user interface for industrial operators or district heating operators, and then they can in that user interface put in their bids, and then the BRP will facilitate that bid gets to Energinet's bidding platforms. And then the other part is the data exchange on what is the actual power consumption of a given unit that delivers ancillary services. And that part in Energinet is not fully up to scale. That means that we are not performing audits in every second on each ancillary service delivering unit. So we have seen when we do sporadic audits on does this battery actually deliver what it should deliver, that it doesn't deliver. It doesn't provide the 1 megawatt AFR upregulation it promised. It only delivered 500 kilowatt. That is an occasional audit we do, but that we need to make fully automatic. So we get a continuous monitoring setup, and that is what Energinet strives towards. Because we need to remember, ancillary services is here to ensure the security of supply of the entire society. So no one can cheat, intentional or unintentional. We need to have this secured with the data exchange. Yeah, that was a quick reflection on that, Grace.
Very good. I think we got the very good point about it. And Gunnar, can you also share with something, because of you mentioned about this EMS and also this other management systems which relate to Power-to-X, and how it can be connect, I mean, and to this kind of like bidding platforms or exchange, which is enable this fast response to the market signal.
So yeah, the good thing is that, as I mentioned in the beginning of the presentation, chemical process industry has a quite long history, and most of the control systems have use standardized data exchange and communication protocols that are also qualified for functional safety and things like this. So we basically have technically good access to the data from these plants. What we are lacking is that so far most of the chemical process facilities are not really active on electricity markets in real time for the fast reacting ancillary services and things like this. So this connection between chemical process data exchange to electricity data exchange, that is not really there yet, but it's more a technical problem because both are ready and we can combine them. Since the area is not so major yet, we actually see more that those actors or those stakeholders that have a plant or a facility up and running, they are a bit conservative with sharing data because it's still quite sensitive. Also for their own business model, it can be a drawback if you are a first mover and share too many of your sensible data too early, and that is more a kind of administrative or legal or non-technical problem that we see there. And but what we are lacking is things like these well-defined terms for estimating the state of a system based on the exchange data, so that we actually know how good is the operating state of the system currently, so that Simon, for example, has a better idea about if I expect 100 megawatt, will I also get 100 megawatt, or will I only get 50 megawatt because half of the system will actually have a state which says not able to operate.
Super, thank you. I think it's since we don't have so much time, if any of the audience have any questions, you can just speak out. Otherwise, the chances just disappear very fast. Great. So we have actually is 2 more questions, but of course you get the contact with all the 3 speakers, and please feel free to contact them. And also we have been asked by some of the audience is whether we can share the PowerPoint afterwards, and I see Simon's knocked ahead, and I hope Gunnar is also good. So then actually is all we're going to be shared with recorded this webinar. Great. So this is the last slide, and thank you all for attending, and also gave a very great presentations, and also the participants. Just want to do a little bit marketing is we have actually the 4 physical upcoming events, and which is 2 is happened in Iceland, and the 2 is happened in Beijing. And especially if you are interested in any of the topic of the summer schools, which is a great potentials for you to get to know more. So thank you all very much, and we will contact you very soon regarding the PowerPoint and also the recorded video of the webinar. So hope you have a very nice day, and especially in Denmark we have great snow. Thank you very much. See you.